Just to emphasize on like dissolves like, I told you molecules that are similar in polarity or molecules that have similar intermolecular forces, IMFs, are likely to dissolve each other. That's what like dissolves like means. And to remind you again, because of dipole moments, the oxygen will be partially negative, which makes hydrogen partially positive, because electrons will reside close to oxygen and hydrogen. Here again, dipole moments, the nitrogen will be partially negative, hydrogen will be partially positive. So the partially positive charge and partially negative charge will attract, and you're going to get a hydrogen bonding, because by definition, hydrogen bonding is a strong intermolecular force that occurs whenever you have H's attracted to oxygen, H attracted to nitrogen, H attracted to fluorine, H attracted to sulfur. Okay, so you're most likely going to get a hydrogen bond right there. So these two, ammonia will always dissolve in water. What about ethanol? That's the line angle structure of ethanol. Ethanol is likely to dissolve in water. That's why you use it to dilute your beer. Oxygen partially negative, hydrogen partially positive. You get again H bonding right there. Intermolecular force. So these two are miscible. What about acetic acid, the active ingredient in vinegar, and water? Same story applies. Hydrogen bonding can occur in between the partial negative charge of oxygen, partial positive charge of hydrogen, right? Same here, because there's dipole moments between the carbon and oxygen. This oxygen can hydrogen bond to a hydrogen of water. Same applies to this oxygen. It can hydrogen bond to a hydrogen of water. So acetic acid or ethanoic acid, so-called, this is acetic acid, C. The acetic acid or ethanoic acid is highly soluble in water because of hydrogen bonding. So those are examples. Now, what if I have hexane 1, 2, 3, 4, 5, 6? So I have hexanes. Will it be soluble in water, or will it be soluble in a molecule like benzene, or a molecule like what we call toluene, or a molecule like cyclohexane, CH2, 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 CH2. So actually, it's not going to be soluble in water because this is highly polar and it's likely to do hydrogen bonding in itself, right? So it will not dissolve in water, but it's going to dissolve in these guys because these are hydrocarbons anyway. And this is a hydrocarbon. So like I said, in hydrocarbons, you expect the intermolecular force to be London dispersive force. So hexanes being nonpolar, okay, and being a hydrocarbon is going to be soluble in molecule 2, 3, and 4, which are also nonpolar and which also experience London dispersive forces. So like dissolves like. So that was just a review of where we stopped. Now let's talk about conformational isomers. These are not structural isomers. When you rotate a bond, because in an earlier chapter, I think chapter 1, we said that sigma bond can rotate without breaking. When you rotate a bond, you're gonna get conformers, like the conformation changes. So it's achieved by rotating about carbon-carbon sigma bond, single bond, and the angle is gonna change. So for example, if you have this molecule, all right, and at the back you have, let me use a different color, and at the back you have a hydrogen up here and then 2 hydrogens down here. So if you rotate it, if you're looking from this end, if you rotate about this bond and rotating only the back, then these 2 hydrogens that are down will be up, okay? And the one that was up is gonna go down. Remember, we are rotating the bond and trying to rotate only the back carbon. We are only rotating the back carbon, this one. So these 2 hydrogens, let me call this A, B, will now be up, A, B, and then this hydrogen C will be down here. And then the front hydrogens, we keep them the way they were. Like I said, you are only rotating the back. So you're gonna end up with this. So these 2 guys are conformers because the placement of the hydrogens just rotated. So we usually use what we call Newman projection. Newman, like new, that's a W. Newman projection to illustrate such shapes. Okay, let me clean up here. I'd like it to be clear. So Newman projection. So you'll have a circle in between because that's where your rotation is happening. Okay, so our rotation happened around this bond. So that bond, you're not gonna see it. It's gonna be represented by this circle. Okay, where you can do rotations clockwise or counterclockwise. The back carbon, the carbon to the back is at the back. You can't see it. So probably this is the uppercase A hydrogen. If we were to put H there, H here, H here, H here, the representation will be like that. So let me again be clear. According to my example right here, so the blue hydrogens will be at the back like that. So actually what you're seeing here is the structure conformation, the first structure conformation right there. You cannot see the back carbon because it's masked by the front carbon. Now, to explain what I mean, I'm gonna show you this structure here in 3D. See, this is the same structure. It's the same structure that I've just drawn. So as you can see, the back hydrogens are down. Those would have been the blue ones, these blue ones, A and B. And then the front white balls are the red hydrogens, which are these ones. Okay, so if you do a rotation around this bond, but this software will not allow me to do that. If you do the rotation, then this hydrogen that's on top will go down, and these 2 will be up, and they'll align with the front ones. Okay. So you're looking at the structure of ethane. Those are 2 carbons. The gray balls, those are carbons. The white small bonds are hydrogens. See, so that will be how the molecule look like. Now, like I said, if you were to look directly, let me see if I can rotate it. Yeah, so if you are to look, so this is the molecule. So if your eye was looking this way, you're not gonna see the bond, you will not see the back carbon. This is what you'll see. See, the front carbon masks the back carbon. So you end up with the Newman projection, where the front carbon masks the back carbon, and the bond you cannot be seen. We just denote it by the circle. Okay, so this is the Newman projection. The circle will be in between the 2 carbons, denoting the bond. Okay, so I think now you understand what I mean by conformation change. So if you were to draw the Newman of this, you'll have the same circle. The blue hydrogens will be to the back after the rotation, and the front carbon will be left the way it was, unaffected. So the hydrogens are still, the two hydrogens are still facing up, but they're going to be aligned with the hydrogens to the back. So this hydrogen will be somewhere here for clarity of drawing. The shape should be a Y shape. So they should be Y, H, H, H. Okay, so this kind of representation where the hydrogens or groups are aligned on the same plane like you see, with no face angle, is called eclipsed. This is eclipsed. But where the groups are spread at an angle like this, an angle theta like that, we usually call this Newman projection staggered. So let's look into that right now. So you're looking at from this direction of the molecule. This is a what do you call it? Ball and stick? No, I think it's a space fill, because this is a ball and stick. So if I put it this way, right? So I'm trying to reproduce this ball and stick. If I fill it up in space, let's see. It's rotating. I don't want it to rotate. How can I stop it? Let me try to stop it here. And yeah, so that's what I think is shown. Yep. So this is what is shown on the notes. So you have this space fill representation, but it would have been clearer if it was either a wireframe or a ball and stick instead of the space fill. So let's go back to, okay, I'll leave it dancing. So if you're looking from this side, then this is a hydrogen, the other one is a hydrogen. This is a hydrogen, a hydrogen, a hydrogen, hydrogen, and these are the carbons. This should be the structure in drawing. Remember, the hydrogen that's dashed should be away. Okay, so if you're looking from the front, this is what you'll see based on this structure space fill model, and which means you have a hydrogen on top and two hydrogens at the bottom in the front carbon. This is the front carbon. Those are the two hydrogens. That's the one hydrogen. To the back carbon, see, there's another carbon back there, the gray. This one, this is another carbon. You have two hydrogens on top, one hydrogen down there. Okay, so this will be the structure. One hydrogen down to the back carbon, two hydrogens on top. But now, if you do the rotation, here, you will get this structure right here, where now all hydrogens are aligned. You move from the staggered form to the eclipsed form. See, the hydrogens are aligned. Here, the hydrogens are filling up the space. It's like two hydrogens to the two hydrogens at the back and one in the front. For these two top hydrogens, the space in between, that's staggered. Now, in terms of Newman projection, avoiding drawing showing the bond and the back carbon, this is what you'll see for the Newman projection. There's going to be a 60-degree dihedral angle between the front hydrogens and the back hydrogens. For the eclipsed conformation, if you're looking straight ahead, you're going to see that the hydrogens are aligned. There's 0-degree dihedral angle and they are crowded. Okay, so the most stable conformation is the staggered versus the eclipsed, because now the hydrogens are well spread in space. Here the hydrogens are crowded, they are too close together. Okay, So this structure is called Newman projection. This is the 3D dash and wedge. The hatched bond means the hydrogens at the back. The shaded wedges means it's towards you. This is the sawhorse where you don't show the wedges. Okay. Now, talking about stability, the staggered should be the most stable of the two. The eclipse would be the least stable of the two. Like I said, the reason is these groups or atoms of elements are crowded close together. You need some angle, you need some space, just like you need your space as a human. Elements and groups attached on the molecule also need their space. Each time there's crowding, there's gonna be strain. So that strain is not good for the molecule. So if you are to consider the relative stability, 60 degrees at 6, okay, this is 0 degrees, right? So at 0, the energy is so high. At 60 degree dihedral, the energy is low, which means the molecule is stable. Now, if you move the molecule to 120, the energy again is going to be high. If you move like these hydrogens move 60 degrees more and keeping the front, you're going to end up with this structure. Let me show you. I'm just trying to describe the angles. So if the hydrogen that was at 60 is pushed further down 60 more degrees, the hydrogen will come somewhere here. And now this hydrogen will be up here at the back. So the bond angle here is 120 degrees. So you will still get an eclipse in that form. If you move this hydrogen 60 more degrees, which makes 180, you get another staggered. You are keeping the front carbon as it is. We are just moving the back, rotating the back carbon. So this hydrogen, let me mark it with an asterisk, which was originally this. This hydrogen, after 180 degrees from the original point, is going to come up here at the back of the circle, at the back carbon. So it's going to end up here, right? And then the one that was on here will end up somewhere here, close here. And then this one that was eclipsed to the other one will end up somewhere here. So you see, you get a staggered. So after 180 degrees, the hydrogen was somewhere here. It moved to 60, to 120, now to 180. It's staggered. So all of these points are going to be staggered. And then here it's going to be eclipsed, conformation, eclipsed. So all the eclipses will have high energy compared to the staggards. And the staggards will be the most stable because they require less energy to exist. The eclipsed, this kind of drawing will be up here wherever there is an E. They'll be having high energy because of crowding of the groups. Okay. So again, which conformation is this? The answer is eclipsed. And it's less stable because these groups, front carbon, back carbon, are crowded. And then this is staggered. Okay. The HH distance in the eclipse is about 2.36 angstroms, which means they are very close. And it's 2.54 angstrom in the staggered. So like from here to here in the eclipse is 2.36. But from, where's the front one? From here to the hydrogen on the back is about 2.54. The longer the distance, the less the sterics, the more stable the molecule will be. Okay. So again, I've talked about ball and stick representation. I've talked about space fill. Now for propane, it's gonna have a CH3 that's larger. So it's larger than a hydrogen. The eclipse is on the left in both sides of the image. So this will be the eclipse, and that's the eclipse still. And okay, so this is the eclipse, that's the staggered, this is the eclipse, this is the staggered. This might not be very clear, but if I can show you the animation, you'll appreciate what we are looking at. But before we do that, let me show you how propane looks like. It's gonna have two hydrogens in the middle, and then you have a CH3 and then another CH3. But for this CH3, I'm gonna draw it like this. So instead of having a hydrogen that we had in ethane, we are switching that hydrogen, this hydrogen, we are switching it with a methyl group, a CH3. So if you switch this hydrogen with the CH3, you get propane. This was ethane or ethane, you get a propane. Prop meaning 3 carbons, and because it's an alkane. So to find how the propane looks like in staggered and eclipse conformation, we are going to look at ball and stick and space filling. So this is your propane. You have 3 carbons, 1, 2, and 3. So if I bring it to align with my face so I can see the Newman projection, I will see that the CH3 tails down, right? See this CH3 right here? It tails down. This is staggered because all the groups, the hydrogens and the metals, these are metal, these are CH3. All the groups are well spread all over the circle, the 360-degree circle. Now, if I do a rotation of 60 degrees, watch where the metal will go. Now all groups are aligned. All the hydrogens are aligned, front carbon, back carbon. This is not very comfortable because, again, there's going to be sterics between the hydrogen and the metal, the hydrogen and hydrogen, this top hydrogen and axial top hydrogen. But if I do another 60 degree, the back carbon, it becomes staggered again, all well spaced up. You do another 60, it becomes eclipsed, which is less stable. So this will be high energy. So whatever I'm trying to describe, let me see, whatever I'm trying to describe is similar to this diagram here. By doing angle rotations, you switch from eclipse to staggered. Okay, so I do another 60-degree rotation, I get that. I do another 60-degree rotation, I move this from the staggered and I go to the eclipsed, and then do one more 60-degree rotation, I get back where I started. Okay, so all the staggered conformation will be more stable than the eclipses. All right, I'll send you links so you can play with it. Let's see. Now, what if you want to look at the structure of butane? So for butane, you're gonna get this kind of structure when you do the rotations of the sigma bond. So if you're starting with, okay, to start with, let me just show you what butane, how it looks like. So butane is one more carbon. So like we did propane, add let's see. So the structure of butane will have one more CH3, one more carbon. So we'll focus on those CH3s because they are bringing more sterics or more crowding. So if you are to draw this structure looking from this carbon right there, you would end up with a staggered conformation. But before we do that, let's just use what we have here. So remember, you have a carbon here and you have the other carbon on the back. So you have 4 carbons, 1, 2, the one on the back, 3, then 4, the one on the top. These two metals groups are very close. This is staggered, well spread out, 60 degrees dihedral angle. Front and back groups, 60 degrees dihedral angle. So it's staggered. So you'd expect it to be almost having zero energy. But because they are too close and these groups are huge, it's going to be less stable than where you have all these groups 180 degrees apart. You see how farther apart these two groups are? This is still staggered, but the big groups are 180 degrees apart, front carbon, back carbon. So that's the most stable. Now, if you do a rotation, you're going to end up with an eclipsed right here, which in turn is going to rotate back to a staggered. Again, this staggered has the two metal groups 60 degrees close, so it's going to be less stable than this staggered. So if you are to rank which staggered conformation is the most stable, this should be number 1, and then these two will be equally stable, and they will be more stable than the eclipses, which will be here, 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 and there. Okay, so rotating the back carbon gives you different drawings on the Newman projection and hence different stabilities. All right, so where the groups, big groups are close together, it's called gauge interactions. That's a G, gauge sterics or gauge interactions. So gauge interactions tend to bring sterics. So this staggered conformation is staggered and gauge or gauge. This staggered conformation is staggered and anti. Why anti? The big groups are 180 degrees apart. Okay. So what about rings? For cyclic alkanes, the smallest ring, of course, is a 3-membered ring. You cannot have a ring with 2 carbons. And the cyclopropane is the smallest ring structure. It's rigid and very highly strained because these bonds are very close at 60 degrees. Remember, we said about the ideal angle. We said the ideal angle on a tetrahedral shape around the carbon, the middle carbon, the center carbon should be 109.5. The ideal angle should be 109.5 for maximum spread of electron groups, which are the bonds. But here the bonds are too close. Remember, 2 electrons make a bond, which means you have the 2 like charges. You have the negative charges of the clouds where the electrons reside in the orbitals very close, and you know like charges repel. So that creates a strain where the bond is trying to repel each other, the bonds are trying to repel each other, the bonds are trying to repel each other. Eventually this ring will explode open. That's why cyclopropane is one of the known deadly bombs, because it readily breaks open, releasing some energy. All right, the outside bond angle is 120. It's larger than 109.5 because the other one is smaller than 109.5 to compensate. Okay, what about cyclobutane? It takes a puckered conformation, like it's not flat. You see how it's puckered? It's not like flat like a square. One side is gonna be a little bit lifted up. So it takes some sort of a puckered shape, bent shape. It's more reactive than a linear alkane, again because of angle strain. All angles here are 109. All angles here are 90 instead of 109.5. The ideal angle again around a carbon should be 109.5 for maximum spread of these electron clouds that are making the bond, the ideal angle should be 109.5 degrees. But now, because it's a ring and rigid, the angle inside is 90. The bonds are too close. You experience bond angle strain. This ring doesn't like to exist. Okay. What about a larger ring cyclopentane? It takes an envelope shape, just like you'd open up your envelope to read your mail. It takes this shape. Why does it take this shape rather than just staying on the plane? The reason is, if it stays on the plane, then it's gonna experience some angle strain. So the bond angles will be not ideal. So to avoid that and to keep the tetrahedral geometry, the ring flips up on one end of the vertex, so that now you get to have these groups almost 109.5 angle spread apart. The bonds are spread apart almost 109.5. Okay, and in fact, there are no 90 degrees. There are no 90 degrees. It should be even, like a pentagon. And the structure should be Packard. The structure should be an envelope shape, okay? To maintain the 109.5 degrees around each bond and to maintain the tetrahedral shape. The most comfortable ring is cyclohexane, the 6-carbon ring. So for this one, it takes a chair shape where, like, you'll sit here, this is your backrest, this is your footrest, and then you'll sit your behind there. So it takes the shape of a chair. The ring is not on the surface. It's not flat on the surface like your book will sit on the desk. No. One side drops down, the other side goes up. So it's not flat. It's actually chair form for the 6-membered ring. Of course, you know which hydrogens are implied. For this carbon, you have 2 bonds, so we have to show 2 more bonds which tend to go to the hydrogens. That's why you have CH2s all over the structure. Now, whenever you have the ring, which of course will take the form of a chair, like I explained, you're gonna have groups that are straight up, we call those axial, or groups or atoms that are straight down, we call those axial down. So this is axial up. These groups in green down here below the frame of the ring is axial down, axial down. Any atoms or groups on the same plane as the chair skeleton is going to be equatorial. This is equatorial up because the bond is tilted up, while this guy is equatorial. This is equatorial down. Okay. So you have to know this general representation of the chair. Only then you will be able to answer questions that relate to chair conformation stability. So it's very, very important. It's crucial and it's a must that you understand it. I can't emphasize enough. You can watch the interconversion of the chairs from here, how you switch from one chair conformation to another chair conformation. But before we do that, let us see what we have. So there's what we call ring flip. It's not a pancake flip. It's not pancake flip. No. If one side of the chair is like this, it just tilts up and the other one will tilt down. So that's what we mean by flip. And I'm gonna play the video in a moment. So the groups that are axial, denoted by A. So this is axial up, this is axial down. After the flip, those groups will end up equatorial. The up and down stays. You're just switching axial to equatorial. All right, so these ones that were axial in red, or is that pink or red? I don't know. Men are colorblind. Will end up equatorial. Okay, ends up equatorial. So like on carbon number 1, the axial up is now equatorial up. The up stay, you're only switching axial name to equatorial. This carbon 1 was tipped up, now it's going to be tipped down. Remember, it's not a pancake flip, it's just a press down. So to flip, you're really pressing down this carbon, and then it forces the axial to be equatorial, and then the equatorial, this is equatorial down, so it's going to end up to be axial down. Axial means straight up or straight down. Equatorial means on the plane as the black backbone of the ring. Okay, so all that process happens on all these carbons once the ring flips. But before we talk about that, let me see if we can we play this link? Let's see if we can play this link. Okay, so I'm gonna take it back and slow the process. So you can see what's happening. So for now, the blues are axial up, axial down. The reds are equatorial up, like for this, and the other one is equatorial down, like that one. They're equatorial because they're on the same plane as the ring structure. So let's play the flip. You'll notice that it's not flipping like a pancake. It's just a tilt. So when the process starts, you're lifting this carbon and bringing these two down. So the red that was equatorial down, now it's axial up. You get what we call a half boat, and then you get the next chair conformation. So now you see all the reds are up, axial, or down, axial. All the blues that were straight up, straight down are now keeping their ups and downs, but they're switching from axials to equatorials. And the process repeats again. So this second chair conformation, we will come and make what we call a half chair, and then a twisted boat, and then a boat right there. This is called a boat because it looks like a boat. You see how the middle bonds are aligned, and then you go back to what we call a twisted boat because it's twisted. These two bonds are now twisted, and we are trying to make again half chair. It's flat, that's a half chair, and then now you make a full chair, and in that case now your blues are back axial up, axial down. So you can play the video over and over again to better see it. Make sure you change your playback speed to about 0.5 or 0.75. Okay, so that explains how you flip groups from axial to equatorial in a chair. Okay, so as the flipping goes, it goes through a boat. This looks like a boat, and then from the boat conformation it goes to the other form of the chair. The rule after flipping, especially if you have big groups, you don't want big groups to be axial. You want big groups to be equatorial, because if they're axial, they create what we call 1,3 diaxial sterics. So for example, assume you have a CH3 here and you have a hydrogen here. If the CH3 and the hydrogens are, both of them are axials, if all these groups are axials, then they crowd either on top or the bottom, depending on where the big group is. To avoid that, you do a ring flip. This methyl group, the Me methyl group, or the CH3, so to speak, the methyl group that was up and axial, will end up down. Will end up up but equatorial after the flip. Okay, and then the groups like this hydrogen right there, let's mark it. That one is up and equatorial. It's not axial, it's not straight up. It's at an angle up, so it's equatorial and up. That hydrogen will end up here, where now it's still up, like it was up, but now from equatorial, it's gonna be axial. So the same process happens with any other group in the chair. Just note that the chair flipped from this shape, the main backbone flipped from that shape, which is this, to this shape. So the chair flipped, and as it flips, the groups will also change their position from axial to equatorial, but they keep their ups and downs. Okay. So, what are geometric isomers? Geometric isomers or configuration isomers are molecules which have the same chemical formula. The atoms are bonded in the same order, but located in different positions in space. That's a key part. Different positions in space. They are not conformational isomers. Conformation isomers have atoms located in different they are not conformational isomers. Unlike conformational isomers, where the atoms are located in different locations in space due to rotation about the single bond, like we did in Newman projection, the geometric isomers are not related by rotation about sigma bonds. This situation arises with cyclic structures. Now, there's too much said here, but the point is simple. If you are to compare this molecule, which is 1,2-dimethylcyclohexane. Okay, so these messy diagrams is actually this structure, and this one is actually this structure. I had to redraw it so we can focus on this area. Okay, so this is not a conformation change. No, it's a configuration change, which is the geometric isomers. These molecules will have the same chemical formula, but atoms are bonded in a different order, located in different positions in space. So whereby you see here the metal right here, the metal right there is on equatorial position, and of course the bond to that metal group is tipped up, so equatorial up. Here the metal is on axial position and it's down, so it's axial down. So if you want to convert this structure to that structure where the only difference is where I've circled, there's no way you can do that unless you break these bonds and then bring them back on. These structures cannot interconvert. They cannot interconvert without breaking of a CC bond. So geometric isomers cannot be made unless you break a bond. But you've realized that with chairs, those are conformational isomers. We did not break any bond, especially from the animation that I just played in the video. There was no bond broken here. It's just a twist and a tipping of atoms up and down, right? So for conformational isomers, there's no bond breaking. But in geometric isomers, you really have to break a bond before you get the other one. Okay, so they cannot interconvert without the breaking of a carbon-carbon bond. So the summary of isomers up to now. Isomers could have different bonding pattern, and that gives you structural or constitution isomers, just like we had butane to 2-methylpropane. Or they could have the same bonding pattern, which will give you stereoisomers, which we'll discuss at length about stereoisomers. And if they are stereoisomers, they could either be interconverted by single bond rotation, like we did with the Newman projections to get conformational isomers or rotamers or chairs, for example, right? Like we played in this video. Or they could not be interconvertible, like we just talked about in geometric isomers, where you have to break a bond before you get the other structure. So that's the summary. So next thing we'll talk about is chemical reactions of alkanes. Practice those isomerism, chairs, flips, and all those things because you're going to be tested.